Okay, let's really get into the idea of curved space today. Let me just remind you of some of the key points that we saw last time. And that was, well, we talked a little bit about, uh-oh, that's not good. We talked a little bit about Newton's view of things and how they change in special relativity. The important thing is that we were drawing these things called space-time diagrams, which include, this isn't just a snapshot of what's happening at one time, it includes the whole history of a series of events. This one happened to represent two masses that were attracted to each other and they ran into each other. And the idea was that we developed is that in the absence of forces, things do the most natural behavior possible. When we view their behavior in space-time, they would travel along space-time, straight lines as they're moving through space-time if there were no forces acting on them. And gravity in the view of special relativity is just another force, and the way I can see that it's acting is that those lines are not straight anymore, they start to curve. Okay? And where we're heading now is into a qualitative description of general relativity where we think of as space-time as not homogeneous. In other words, it's not, unlike this plane that we were looking at back here, it's sort of the same up in this corner as it is over there and down there, other than the artificial axes that I put on it. That's not true anymore in general relativity. There's going to be some curvature, and we'll talk about that a little bit today. More importantly, gravity is not like other forces. We're going to find out that in the context of general relativity, that particles that aren't too massive anyways, that they don't distort space-time by themselves, they tend to still travel along straight lines. And so even though all particles are traveling along straight lines, as long as there's no non-gravitational forces, we'll still see the effects of gravity that's evidenced by the curvature of space-time. So where we're going to go today is first just talk about, because it's easier to think about, just the geometry of space itself without involving time. And then we'll generalize later to thinking about curved space-times. So a little bit about curved spaces and uncurved spaces. Here is a flat plane space, and we're going to mostly be visualizing two-dimensional surfaces and spaces because they're easier to draw. Our space, of course, is three-dimensional, but it's hard to view a curved version of our space. Either draw it or visualize it in your head, whereas we can easily do that with two-dimensional spaces. So we're going to contrast a flat plane space with other spaces that have different geometries. I've got a sheet of paper up here, and you should imagine this space going on forever and ever. It's not like it has edges. I just didn't know how to draw it without edges. You wouldn't see anything. So we're going to imagine that there are some creatures who are inherently two-dimensional creatures, and they're stuck inside this space. There's nothing they can do to leave. They can't hop out of the space and come back into the space. I think you read a little bit about that in Lepoidovin for today. And they're going to understand the geometry of their space, in other words, the shape of their space, by measuring distances between points in their space. And one important thing is that, we may think that this space and this space, one that's curved around like this into a cylinder, are really different spaces. In fact, you may be tempted to call this a curved space because it's curved around in a circle. But the important thing here is that these Pac-Man creatures that I've drawn on here wouldn't know the difference between this space and this space. It behaves exactly the same. In fact, even if I took this piece of paper and crumpled it up into a little ball, they wouldn't know the difference because the only way they can move around is within this space. And so when they try to go from this point to this point over there, they never jump out of the page and go over to that point. They have no idea that in our three-dimensional world, those 2 points are close together. They're still far apart for those two creatures, right? So we're going to imagine that for them, their whole world is that space. So when I curve around that piece of paper, there's sort of a superficial difference between those two spaces, but in terms of their geometry, we're going to consider the geometry the same. Sometimes people will, I don't know that this is universally used, but this term extrinsic versus intrinsic geometry, we could say that this flat plane space and this curved, at least in quotes, curved cylinder space are different extrinsically, and that they're not embedded in our three-dimensional space exactly the same way, but intrinsically, in other words, to a being that's living within those spaces, they're exactly the same space. There's no difference between them. So we would say they're the same intrinsic geometry. And just for simplicity, that's all we really care about here, is what it feels like to be a creature living in that space, just like we're living in our three-dimensional space. So we're just going to say they have the same geometry, even though they look a little bit different. So contrast that with the surface of a sphere. So I brought a basketball so we could draw some lines on it or think about it. We'll think more about that later. But in comparison to this, there actually are really differences to when you live around, move around in these two spaces here. First of all, this one, there's only a finite amount of surface area. We're talking about not the volume inside the ball, but just the surface of the ball. That's what mathematicians call a sphere. Sometimes if you want to be clear, you would say the surface of the sphere, but to a mathematician, the sphere is the surface of the sphere. But I put that there just to be clear. So, a little Pac-Man creature walking around on this surface would find that there's only a finite amount of area they could visit, whereas up here, at least unlike the way I drew it, there's really an infinite amount of area to be explored up there. But there's a lot of other interesting differences that we'll get into today. Similarly, here's what might have been a flat plane, except it has some kind of bump that's been pushed into it. It's like a rubber sheet and someone's pushed their finger up into it, right, and made a little bump in the middle of it or something like that. These three all have different geometries. That means different intrinsic geometries. They're different to a creature that's sitting inside. Okay, so we're going to imagine that in our world, we're not used to imagining things this way, but to a creature that's living inside one of these spaces, there's nothing but the points in the space. So it's easy to forget that if you imagine, oh, here's a point up above the north pole of this sphere. No, if we're talking about the geometry of this sphere, that point doesn't exist. There is no such point. And similarly, there's no center of the sphere. Those creatures can't point to a center of the sphere. And really, in some real sense, there is no center of the sphere. You might say, well, they just don't know, they can't see it. But when we're considering the geometry this way, there's nothing in the world except this two-dimensional space. It's not like it's sitting in a three-dimensional space. So that point P2 at the center doesn't exist. It's kind of like in Euclidean geometry. Here's a point floating above the Euclidean plane. When you think about distances between points in the space, you never consider going along a path that jumps out and jumps back into the space. That would be ridiculous. So that's the idea of considering only the intrinsic geometry. So I'm going to draw some pictures with Pac-Man creatures just because they're two-dimensional. So here's Mrs. Pac-Man. She can move around the space and measure some of the properties. And we're going to investigate some of the differences in the properties that she would find out by moving around in this space versus moving around in this space, beyond just the finite area of the sphere. Okay? How is she going to find out that she's living in a non-Euclidean space? In other words, this is not going to satisfy the postulates, all the postulates of Euclid's geometry, and we're going to find out exactly what goes wrong in there. That's what she's going to do. She's going to walk around, make measurements, and see if the familiar properties of measurements that we expect to be true are actually true. And we'll detail that in just a second. But if Euclidean geometry kinds of measurements hold, she will conclude that she's in a flat plane. But if something that doesn't follow from Euclidean geometry holds, she's going to conclude that she's on the surface of a sphere. Now, an important distinction here, again, it's the same as the difference between this plane and this cylinder being extrinsically different, but we still say they're the same geometry. It's the same way with the surface of this beach ball. It doesn't matter if the beach ball is fully inflated, so it looks like a sphere, or partially deflated, or completely deflated. To a creature that's living inside the surface of that beach ball, the surface is exactly the same. Just to show another example, here's a ping pong ball that someone has destroyed and pushed a little divot into it like this. But we would say these surfaces, you know, as long as in the process of pushing it in, you haven't really stretched the material so that you've deformed it, and usually you don't to any significant degree when you do that. Here's a rubber ball that I partially deflated that my kids don't play with anymore, but we would say, you know, this surface has the same geometry as a perfect sphere. If you moved around in here, when you move through that little divot in there, you're not going to see any difference or sense any difference, be able to measure any difference from a fully inflated sphere. Okay, so in order to test the properties of Euclidean geometry, we have to know two things. First of all, what it means to measure distances, because she is going to determine what kind of space she's in by measuring distances and maybe some angles. Presumably she knows how to measure angles, but it's not clear how to measure distances in this space up here. We need to specify that. And secondly, how she decides to move along what we're going to call a straight line in the space. And you may say, well, in this space there's no straight lines, but actually there are straight lines. They're perfectly straight. They just don't look that way to us because of the way we've embedded it in our three-dimensional space. So let's first talk about one, how to measure distances. So you already know how to do this in a Euclidean space. In other words, using plane geometry. Of course, one way to do it, you know, just that's a little bit more visually appealing is if you were that Pac-Man person inside there and you wanted to measure the distance between 2 points, you'd take a piece of string and attach it to the two ends and pull it till it was taut, right? As tight as it could be, and then you could measure the length of that string using your rulers that you have in the space, okay? The tape, of course, is going to lie along what we would call a straight line. The same thing's true if you're living on the surface of a sphere. So here's a non-Euclidean 2D space, the curved surface of the sphere. How do we measure the distance between P1 and P2? You're supposed to be visualizing them as being on the surface. It's kind of hard to tell there. What we would do is attach a string between the two and pull it until it's taut. But we have to remember that string's not at liberty to go out into 3 dimensions because there's nothing out there. It looks like there's something on this, in our world, the straight line connecting P1 and P2, right? But we would say in that world, there is nothing in that space. There's nothing to talk about. There are no points out there. It's not that they don't get the idea. It's just that it's not there. There's nothing out there. Okay, so there's another line segment between P3 and P4, and you're supposed to be, again, envisioning those as being on the surface of the sphere. You can't take a shortcut between those 2 points any more than these creatures would know that P3 and P2 are close if we put them like this. We should not use the terminology that says P3 and P2 are close. They're not close. They're still far away. 16.5 centimeters from what I wrote on here. Okay, so we could say a taut string is the closest thing to a straight line, but I'm going to make an argument that it actually is literally straight, even though it doesn't look straight to us. That's just an illusion, okay? These straight lines inside of a space, which is you take a string and you pull it as taut as it can get, it's called, those things are, in the context of geometry, are called geodesics. A curve that goes inside a space is a geodesic. That's a straight line, okay? And so you can draw lots of curves that wind around in a space. Here's one that's winding around in some crazy way. It's clearly not a geodesic, if you can envision what the shape of that is. If you pulled it taut, it would shrink to a much smaller length. Okay, so geodesics correspond to the same thing that we do. You know, if I'm going in a certain direction, if I'm standing at a point in space and heading in a certain direction, there's only one way I can go that is the straight ahead direction. And that's also true for Mrs. Pac-Man sitting inside that sphere, or even inside this randomly kind of curved space like this. If you're headed in one direction, say you're standing at this point right there, there's only one direction you can go that's along a geodesic. Now, this isn't a geodesic that's pictured up here, but here is a picture where this purple path and the orange paths are supposed to be indicating geodesics. Sometimes, if you're really worried about the detail, there's if you're at a particular location and you draw a tangent plane to that, this won't be important for us, but if you know what a tangent plane is and you project the curve onto the tangent plane, then a geodesic should project to a straight line on that tangent plane. But in any case, it's the straightest way you can go. And that's what I said there. So we get some very interesting straight lines. So here's a donut-shaped surface called, mathematicians call it a torus. We're talking about just the surface of the donut, not the interior. The interior doesn't exist. And if you're standing at this point on the donut, Mrs. Pac-Man's sitting there, and you tell her go straight ahead in this direction, she starts winding around the surface of the torus in some sort of corkscrew shape that turns around. Those are geodesics that she could walk around. The collection of all straight lines is the collection of all geodesics. Okay. Now, as I said, despite how they appear, the geodesics are actually perfectly straight. It appears that if I draw a curve, so here's a straight line curve on this plane over here, and I'm trying to draw the same straight line segment on this curved version, which we said is exactly the same geometry. And you may say, well, Miss Pac-Man's going to know because as she travels along that line, she's going to sense that she's turning to the right as she goes from the front to the back. But that's actually not true. In fact, it appears to curve, but it's actually perfectly flat. And in fact, you could imagine curving it the other way. And of course, Mrs. Pac-Man wouldn't know. She's heading to exactly the same points in space. Now she's turning to the left if I just look at it curled up in a different way, right? She's not going to know the difference. It's the same way. Uh-oh, that's not good. It's the same way with curved surfaces. Interesting. I don't like that. I feel like this happened once before to me, and I can't remember what fixed it. It's something about the keyboard getting stuck. Pardon me. I may have to close and reopen this presentation. Let me just start it again and see if we're okay. Oh, you're holding down the control key. This keyboard must be faulty. Okay, it still thinks I'm holding down the control key. This is exactly what happened to me a couple of weeks ago. And I don't know if I'm ever going to get it out of here. It's still... See if I hit the control key a couple of times. Nope. Okay, we're going to have to look at it just like this, and I apologize for this. I'm not sure. There's some problem with the keyboard here. I'm going to try to show this in such a way that we can see as much of this as possible, but it may be that the only way that I can click through. No. Maybe if I turn this off and turn it on again. Yeah, that's an idea. Of course, the question is, can I actually see where the keyboard connects in this? It's one of these two. Sorry, Zoom folks, just hang on for a second. Let me see if I can. There's something going on with the keyboard, and I'd like to get it fixed so that I can actually point at the presentation. Still not working. I don't know what to do about it because maybe if I take that thing out and put it back in. Still behaving strangely. And unlike before, it won't let me advance the slides the old-fashioned way either. Okay, so it thinks I'm holding down the control key. I really don't want to reboot the computer because I'm going to have to kick all the Zoom folks off. Something's stuck on the keyboard. Hey, something's working now. Whatever I did, just slamming on the keyboard worked. So we'll go with it. Let me find where we were. I apologize for that. That's the problem with all the technology. Okay, so we were talking about going along in straight lines, and I was going to try to convince you the same thing for a sphere. All right, let me see if I can do slideshow mode now. Okay. Let's see if this works now. All right, I'm back. I don't know. I think my fancy remote is really messing this system up. Somehow it gets it jammed. What I was going to say, just like in a flat plane, we already know what straight line segments, or now we're going to call them geodesics, are for that kind of space. On the surface of a perfect sphere, the geodesics are what we call great circles. They're the biggest circle you can draw on that surface. In other words, if you imagine that you're in 3 dimensions relative to this, and so that you can envision what the center of the sphere is, you know, for the creatures who live there, there is no such point. But they're circles that are centered on the center of the sphere. So they're the biggest circles you can draw, not a little tiny circle that would, you know, just go like this. The great circles are like something going around the whole sphere, what you might call the equator kind of curves or whatever, okay? So just like Mrs. Pac-Man isn't gonna notice that she's curving around to the right there, you might think that Mrs. Pac-Man in this case for sure is gonna notice that as she rounds the top, that she's sort of curving towards the bottom of the screen, but she won't notice that at all. As we said, we could indent the top of the sphere without changing the intrinsic geometry of the sphere. And if she follows that same curve, if I try to draw that same curve on there, I've done that in red as best I could on the computer. She is now, you might say, when she, here in this case, when she passes what we might call the North Pole, she might think she's curving downward, but she's not going to have any idea of the difference in the geometry here, and she'd be curving upward. So she's curving neither upward nor downward. She is going literally straight in the space. She doesn't have any sense of not being able to go straight, and we shouldn't think that there's a sense in which she can't go straight. Okay, so that's the idea with geodesics. You know, it's the same kind of idea as if I had this deflated ball. Let me push some of the air out of it. And I'm hoping those of you on Zoom can see me on the little camera so I don't have to switch screens. If I draw a geodesic roughly on there, that's this great circle that's going around there, and it's the same as if I dimple it in like that. I'm neither curving down nor am I curving up as I pass through that region that I've sort of buckled in like that. I'm actually going literally straight, not just the straightest I can, but absolutely straight. Okay, so every at least smooth space If there are kinks, you might not know which way to go straight, but every smooth space has its own geodesics. So here's a space that happens to have just like a little bump in the middle of an otherwise kind of planar space. These donut toruses have their own geodesics. Okay, so the question I want to address now is 3 different answers to what sort of measurements can Mrs. Pac-Man make to find out which of these geometries her world has. So we're going to compare Mrs. Pac-Man moving along the surface of a sphere versus a flat plane versus a saddle surface space. Saddle surface space is sort of like the shape of a Pringles potato chip, if you know what that is, or the shape of a saddle on a horse. And it has different properties than this other one. This looks like a disc, but it's actually supposed to be a spherical surface. So what she's going to do is test the theorems of Euclidean geometry, and I'm assuming these sort of basic ideas you've all heard of before, okay? So for example, she can use a string of length r to draw a circle and measure its circumference. We'll call the circumference c. We already know what that means in the context of a flat plane, and when she does that, she's going to find that the circumference is 2 pi r, as we expect, as we've learned and memorized from long ago. Not so on the surface of a sphere. Suppose we put the center point, the point at which she's going to attach one end of the string, pin it down in the space, and then she's going to walk around with the string taut. So she attaches one end of the string, somehow pins it to the space there, and then stretches out the string taut, and then she's going to walk around the surface of the sphere while keeping that string taut. Here's one circle she could draw. This circle happens to be like, it doesn't have to be that big of a circle. She could have drawn a smaller circle, but in this case, it's pretty clear that the circumference, I hope, in this case, is not going to be as big as we would expect it to be if you were sitting in a Euclidean space. In other words, that radius that she's drawn is much longer than what we would normally think of the radius of this circle, but this point in the middle isn't even in the space. And therefore, she's going to measure, when she compares the distance around the circumference, she can measure that with her rulers, versus the radius, that the circumference is greater than 2 pi r. Okay, that's what's going to happen on those spherical kinds of surfaces. Similarly, if she does the same thing in this hyperbolic saddle-shaped surface, Pringle-shaped surface, she's going to find out that in this case, because the surface as you go around is sort of wiggling up and down as you go around, you're drawing out too much circumference in this case compared to the radius that you're at. And so the exact opposite is true there. The circumference is bigger than 2 pi r. And therefore, this is one way she can find out the difference between these kinds of geometries, whether she's in a saddle-shaped space or a sphere-shaped space or a flat plane space. Another theorem of Euclidean geometry, the sum of the angles in a triangle are 180 degrees. Well, that's true in a Euclidean plane, the flat space that we see there. You add up the angles measures, and you'll see they sum to 180 degrees. Whereas on the surface of a sphere, if you look at the angles in the triangle that's drawn here, maybe if this were in a flat plane, these would be equal, 60 degrees angles. We're trying to make equal angles. Well, maybe it's worth showing this, unsharing the screen to make me bigger here and draw on this surface of the sphere. So if I imagine drawing a triangle means 3 straight lines. That means that they've got to be great circle segments. What I could do is start at the North Pole here and go down to the equator, turn by 90 degrees and go along the equator to a point that's a quarter of the way around, and then turn by 90 degrees again and go up like this. This is literally a triangle in this space, but each one of those angles is 90 degrees. It's a perfect right angle in the 3. Right? So in this case, the 3 angles would add up to 270 degrees, more than 180 degrees. And so that's an indication that Mrs. Pac-Man is sitting in a non-Euclidean space. Okay, similarly, with this saddle-shaped space down here, you can see that the triangle that's drawn there, it looks like the angles are going to add up to less than 180 degrees. And in fact, they do add up to less than 180 degrees in that case, because they're sort of pinched in at the ends. So that's another clue, another result from Euclidean geometry. It's called Euclidean geometry because it's describing the properties of a Euclidean space. The sphere surface, oh no, that doesn't seem good. Oh, there we go. Maybe I was too far away. The sphere surface and the saddle surface are what we would call non-Euclidean spaces. They don't satisfy the axioms of Euclidean geometry. Okay, one final case here is the famous parallel postulate. If you've studied Euclidean geometry before, you know there's lots of talk about the parallel postulate and how suspicious it is. And that was the postulate that was first discovered in a way to think about non-Euclidean geometries, to loosen the parallel postulate so it wasn't true. So the parallel postulate in the context of Euclidean geometry says, given a line and a point not on it, so I've drawn a line here in this Euclidean space, and a point not on the line is the red dot. There's exactly one line through that point not on the original line, which does not intersect the other line. That's one statement of the parallel postulate. In other words, this is not a parallel because it clearly intersects. This one's not a parallel either. There's only one angle that, as I twist that line through all possible angles, there's only one angle that succeeds in never intersecting the other line, if we imagine this plane going on forever. That's not true on the sphere anymore. So here I've drawn at least part of a line. It was hard for me to draw in PowerPoint, but this is supposed to be part of a great circle going from the North Pole to the South Pole. Here's a point not on that line, and here I'm drawing another line that goes through that point. And it intersects it at 2 points. And you can imagine, no matter how much I try twisting that angle around at which I'm drawing the line, the geodesic, the great circle through that point on the right, I'm not going to avoid running into the other line if it's continued on far enough, because they're always going to meet. Two great circles always meet at 2 different points. So there's no parallel that you can draw up here. Similarly, for the saddle-shaped surface, if you look at this construction down here, here's a line. Okay, it's sort of curving like this. I can draw a point that's not on that line, and then here's one example of a parallel, but if I adjust the angle of that a little bit, if I change it so it goes through that point at a slightly different angle than the one I've drawn here, it still is going to avoid it. And that's because the space, those lines were sort of, in a sense, diverging from each other as they went through. So if you find there's one and only one parallel, that's a sign you're in the Euclidean space. If not, you're in one of these spherical spaces or saddle-shaped spaces, depending on which one of those 2 cases hold. An infinite number of parallels or 0 parallels. Those are the 2 other logical possibilities. So in the context of 2-dimensional geometry, you can really talk about 3 different kinds of homogeneous geometries. One's called elliptic geometry. It talks about the surface of a sphere. Euclidean geometry is the more familiar one of a flat plane. And hyperbolic geometry, if we consider this space having kind of the same shape everywhere, even though that's a little bit difficult to visualize here in this saddle-shaped picture, that would be called hyperbolic geometry, depending on which way those axioms hold or fail. Okay, so just to summarize here, of non-Euclidean geometries, the geometry of spaces that are not flat is called non-Euclidean geometry, and there are many varieties. In 2 dimensions, things are simpler. There are only 3 different varieties, or sort of the flat case, the Euclidean case up here, is sort of right in between these 2, right? It's the difference between some of the angles being less than 180 degrees and greater than 180 degrees. Okay, so Euclidean geometry, I know for those of you in the class here, the font is a little bit small, but it says Euclid's parallel postulate holds, interior angles of triangles add to 180 degrees, C equals 2 pi r. The familiar things happen there. For elliptic geometry, that's like the geometry of the surface of a sphere. the parallel postulate fails. There are no parallels to a given line. Angles add to greater than 180 degrees in a triangle, and the circumference is less than 2 pi r, and kind of the opposite thing for hyperbolic geometry. The parallel postulate fails in a different way. There are infinitely many parallels. Interior angles of a triangle add to less than 180 degrees, and the circumference is greater than 2 pi r, okay? That's the way Mrs. Pac-Man's gonna find out, by just exploring around in her space. And now imagine we're in three-dimensional space. If our three-dimensional space is not a Euclidean three-dimensional space, we can do similar kinds of things. We can measure angles between, draw a huge triangle and try to see if the angles really add up to 180 degrees, or are they a little bit bigger or a little bit less. Now, the important thing as concerns general relativity, Einstein's theory of gravity, is that these are homogeneous geometries. In other words, the idea is every point in this space looks like every other. Every point on the surface of the sphere, at least when you draw it in that symmetric fashion, it looks like every other one. It's harder to imagine for the saddle space right here, the way it's drawn, but you can imagine a geometry where it's completely the same from point to point. Every point is identical. We're going to be interested in a more general kind of geometry where the shape or the curving of the space changes from point to point. At one point in the space, it may be more like a surface of a sphere. At another point in the space, it may be more like the surface of a saddle, and it might change. So for example, and I know it's a little bit difficult for those in the room to see, but I'm looking at the lower left corner here. This is someone's vision. Ignore the spheres and things on there. I'm just interested in the shape of the surface that's being plotted below them. If we look on, well, sort of underneath the surface of this sphere, we're sort of at the bottom of a depression in the surface. That's like the surface of a sphere, right? It's going to be sort of rounding up in all directions as you go around. So that's going to be more or less like the surface of a sphere. That's why it has elliptic geometry there. So there's an elliptic region of space. Space looks a little bit different there. It's elliptic. As I go up to the edge where this flat part is sort of turning over to the bottom of that little marble down there sitting at the depression, I hit a hyperbolic region. And that means that if you imagine going over that edge, I'm going to kind of talk to the camera, maybe they can see me in the small view. As I go over the edge, the surface is curving in one direction as you go, it causes you to go down into the depression, but in the other case, it's curving in the opposite direction. So it's kind of like that potato chip or saddle surface that if you move in one direction, it curves up. If you move in the other direction, it curves down. That's one way to see that you have a hyperbolic geometry, at least in a two-dimensional space. It's the same way right on that edge there. It's sort of, as I move, if I go around that circular kind of place where it starts going down into the depression, it's curving in one way, but whereas it's curving in the opposite direction as I head straight down into the depression. And here's a region over here that looks like, oh, it's almost perfectly flat. So there's a flat region. Lots of different things. When you put all these together and you allow the shape of the space or the curving of the space to change from point to point, that's called Riemannian geometry. Although there are different names for these. Riemann was the first one, I think we read about this in Lepoideman's reading. He was the first one to investigate the geometry of a sphere as a non-Euclidean geometry. So sometimes people call spherical geometry Riemannian geometry too. But later on, he went to describe these more general kinds of geometries, and that's what he's more well known for. And the hyperbolic geometry, sometimes people call that Lobachevskian geometry. And can I bring up the other name? We heard about someone else in the Lepoideman reading. Bolyai. Bolyai and Lobachevsky were two of the first to describe the kind of geometry of this space as an alternative to Euclidean geometry. So you'll see that described as Lobachevskian geometry sometimes. But it's more suggestive to say hyperbolic and elliptic, I think. Okay, so this, where the geometry is changing from point to point, is what we need to describe general relativity. We've been talking about space being homogeneous, and all of these properties that are being argued over by Leibniz and Newton and Clarke being dependent on our intuition saying everything's got to be the same everywhere. As I move over, if I move everything every physical object 5 feet to the right, nothing's going to change. Well, that's not true if this is what we're talking about as our background space, right? If an object is here and I move it 5 feet to the right, it all of a sudden is in a region of elliptic geometry where maybe it was sitting in one of hyperbolic geometry, and that makes a difference. You can tell if you've been moved to the right. So, of course, we can't blame people in history for not having this perspective because we live in an age where we happen to be lucky enough to have been born into non-Euclidean geometry being well known. Okay, I can't remember exactly why I put this slide in here, but I feel like it was something about that was either in the reading or it was a reading response question. But the idea is, here's Mr. and Mrs. Pac-Man, and maybe they've fallen in love and they're concerned about the distance between them in this space. Nothing changes in their particular region of space, but something can happen in the intervening space between them. And I guess what I wanted to point out is, first of all, just by knowing the properties of what's happening near Mrs. Pac-Man and near Mr. Pac-Man, you have no idea about what's happening in between. Lots of stuff can happen in between. The second thing is that there may be more than one straight line between these two. In other words, if I am going to go from Mr. Pac-Man to Mrs. Pac-Man, they hold a string and they try to stretch it taut. One way is it might go around the mountain this way. But they could also stretch one taut around the back of the mountain. And they might even be able to stretch one taut going over the top of the mountain if they balance it very carefully on the top of the mountain. So it doesn't have a propensity to be pulled down one side of the mountain or the other. So one of the other things that can vary in non-Euclidean geometries is that there's more than one straight line between pairs of points. Okay. And so that's our sort of side byway into just the geometry of space, where we're thinking of space. Now we're going to go back to including time. Remember our space-time diagrams. Those space-time diagrams for general relativity and for Newton are flat. But we're going to start allowing them to curve and think about the consequences of that. And I apologize, I don't have a worksheet to work on today, so I know I'm talking an awful lot, but this is sort of an exceptional case, hopefully, for the course that way. Okay? Curved space-time replaces a gravitational force. Okay, what motivates the curvature of space-time in general relativity? Well, it's something called the equivalence principle. And the equivalence principle, when combined with special relativity, the equivalence principle says, under only the effects of gravity, in other words, if I am holding an object here, here's a piece of chalk, it's not only under the effects of gravity. I know this isn't a physics course, so we haven't necessarily talked about forces a whole lot, but there are two forces being exerted on this piece of chalk. Gravity is trying to pull it down. It's applying a force downward, but my palm is pushing upward on it. So it's not only under the effects of gravity. Being only under the effects of gravity looks like that. When you're in free fall, you're dropping freely. Okay. So the equivalence principle says an object's subsequent motion, when it's only under the influence of gravity, only depends on where it is and how it's moving at that instant. Okay, well, that doesn't sound too surprising. But the thing that is surprising is that its subsequent motion doesn't depend on its electric charge, its mass, the color of the object, any other intrinsic features of the object. Pianos, marbles, all those kinds of things behave the same way under the influence of gravity. And you might say, aha, a feather doesn't behave that way. But when a feather's falling, the air resistance really matters. So we wouldn't count it as being only under the influence of gravity because the air is delivering a significant force to it on the same order as gravity. So a feather wouldn't be a good example of that unless we removed all the atmosphere from the room. Okay, so another way to put this is an object's world line. Remember, the world line is in the space-time diagram, how the object is moving around in space as time goes on. If it passes through a certain event with a certain slope, remember in our space-time diagrams, the slope represented how fast it was going, at least from a certain person's point of view. A vertical line meant at rest. That was from a certain IRS point of view, right? And the more it was sloping, the faster it was going from that person's point of view, right? That was a faster speed in the space-time diagram. So the idea is, if the subsequent motion only depends on how fast it's going and its current location, if an object's world line passes through an event with a certain slope, that information completely determines where it's going to go for the rest of time. And we don't care what the object is, whether it's a grand piano or a marble or any other object, as long as it's only under the influence of gravity. So the idea is, at least in our old view of space-time, we can imagine here's a particular mass that happens to go through this event E1 there. There's nothing special happening at E1, but remember, an event is just a point in space-time. If we let another particle go that passes through E1 with the same slope on its world line, it can't ever diverge from the world line of M1. They're both going to move together for the rest of time. Or if we did subsequent experiments where we released one and then we released the other one, they would both have exactly the same orbit or trajectory as a function of time. Okay? So what this means is that gravity determines the preferred world lines on which all objects follow, regardless of their composition, and especially important for us is their mass. So a proton in a piano will, given the same initial position and velocity, follow the same trajectory around the sun. In other words, if you start them going the same way, so they have the same initial position out there in space and the same initial velocity, even if they're on a crazy elliptical kind of trajectory, they'll follow the same exact location as a function of time. And because of that, because it doesn't depend anything on what it is that's following it, it seems sensible, and this is Einstein's great insight, is that that's not really a property of the object so much as it is a property of space-time itself. In other words, the piano and the proton that are both orbiting Earth are both doing the most natural thing possible, because it doesn't depend what you put there, it's going to go in the same way. So it seems like the path it's following is determined by space-time itself and not the objects that are following through it. Okay? So Einstein is thinking that the world lines are the paths of least resistance. In other words, they're the straight ahead direction. If you just give something a flick and it starts going, it just keeps following a geodesic, assuming there's no other forces on it. If there's electric forces or magnetic forces or other kinds of forces, it will change from a geodesic. But those world lines, and these are going to be four-dimensional world lines, because remember, we live in a three-dimensional space. If you were in a one-dimensional space and you draw it as a function of time, you get a two-dimensional space-time. If you live in a three-dimensional space and then you add time to that, you would have a four-dimensional space-time diagram. So what Einstein is thinking is that the natural paths, in which case gravity, even when gravity is acting on something, the natural path all objects will follow are geodesics in a 4D curved kind of space-time. And the curvature mimics the effect of gravity in the sense that we're going to talk about in just a minute. Okay, so objects that are apparently under the influence of gravity are really just following geodesics in a curved spacetime. You can't do that with electric forces or other kinds of forces because certain objects aren't subject to electric forces, right? If an object has an electric charge, you can put an electric force on it. If it doesn't have an electric charge, there's nothing you can do to exert a force on it. So that means the charge is going to affect whether it goes this way or that way in space. But that's not true for the gravitational force. Jack?
This makes a lot of sense to think about for like orbits and stuff. But you can imagine different velocities giving different solutions for the curvature of space-time, right? So in other words, the orbit something is on is not the only solution. It could be going, faster or slower depending on that.
Yes, this may be easier. So the question was, if you have a particular curved shape of our space-time, there are lots of different orbits that something could follow, right? I could flick it in different directions, and maybe in one case it goes out of the solar system, in another case it orbits the sun, in another case it crashes into the sun. Those are all different cases. Of course, we wouldn't want to include the part where it hits the sun, because then it's not just under the influence of gravity anymore. And those will probably be easier to visualize in, when we draw some pictures of these curved spacetimes. But maybe if I take the risk and try to just draw over here on the part of the board that people can see the way I've got the camera, that even if I have a flat space-time diagram, so there's position and there's time, a single particle, at time t equals 0 could be at this location and just sitting at rest from this person's point of view. It could be at this location and heading in that direction. It could be at this location and heading up in that direction. So there are lots of different trajectories. Now notice that at least in terms of this space-time diagram we have right here, all of these curves are geodesics. So that's what Einstein is claiming. Look, a straight line is just a good old-fashioned straight line if you're sitting in flat Euclidean space. So all of these lines are geodesics, and the claim is that it doesn't matter if this is a marble or a piano or something else, doesn't matter what its mass is, doesn't matter what its electric charge is, as long as the only force that's acting is gravity, and in this case this is going to be the case where no gravitational forces are acting, then it's going to follow a geodesic in that space, and the space won't have any curvature. But when gravity is included, and anytime there's mass around, there's going to be gravity that's included. The space-time is going to be curved, so it's a little bit more complicated. But we'll see those kinds of pictures in just a second. And I've lost control again. Let's see. So it's important to remember that we're talking about the geometry of space-time now, not just the geometry of space that we were talking about earlier. So it's not three-dimensional space. So you might, mistakenly think, oh, I've seen pictures like this before. This must be what we're talking about with curved space-time right here. No, this is not a picture of space-time. This is just a picture of some kind of space. And so someone's put a fanciful kind of picture of curving on here that gives you an idea that things might go around in circles. But this is not a space-time diagram. So when we talk about the curvature of space-time, we're not talking about this kind of picture, because notice that, I guess this isn't really well illustrated here, but if we imagine this comet that's flying through the universe hitting this event or this point in space right there, and it's going at a certain angle, there might be another object that wasn't going as fast, but it was sort of on the same path right here, but it was going to continue going around in a circular orbit around the sun. So we're not talking about this. If you go through a certain point in space, that doesn't mean that you're going to continue even in the same direction. It doesn't mean you're going to continue on the same path, because you might have been hitting that point at a different speed. If you hit it with a faster speed, you might get thrown out of the universe. If you hit it with a slower speed, you might go into an orbit. But the claim is when you generalize this kind of picture to space-time, that's not going to happen. Okay, so how do we visualize the effects of gravity in a curved space-time in a simplistic kind of way? We're not going to do the mathematics behind all this curvature and stuff, but just to visualize it, okay? So this Minkowski space-time, that's another name for the flat geometry of special relativity. If we have nearby objects A and B, and they're moving with identical initial velocities, in this case, I've given them 0 initial velocity from the point of view of the IRF where I'm drawing these world lines, right? They're at rest with respect to each other. They're not going to move toward each other. And so that means in flat space-time, there's no gravitational effects. Nothing, even if these things had mass, we can't describe the fact that they're going to be attracted to each other and eventually run into each other. We can't describe gravitational effects. So in a sense, this Minkowski or flat space-time of special relativity describes the case where gravity is just being ignored. It's not an important force. But gravity is an important force, and you can at least in some way see that if you have a curved space-time. So this is not space now. This is not a space you can move around on. I'm imagining here's a little bit of an x-axis. This is someone who lives in a one-dimensional world, and they can move along this little line here. And this is the time direction going up vertically right here, right? And we imagine, okay, I stretch a straight line between the two, and then I have the two sit at rest initially. And I say, keep sitting at rest. And they do that. They follow their geodesics, just sitting at rest, and they're eventually going to collide up here. So having a curvature to space-time can actually mimic the effects of things getting closer together or actually farther apart, which it doesn't seem like it would do with gravity, but sometimes things actually get farther apart under the influence of gravitational fields. We'll see if we get there today, okay? So they move towards each other. That's what happens. Here's another object that started out at that same initial time, which corresponds to space being this line segment right here. And it happened to be moving to the right in this one-dimensional world. It happened to be moving to the right. But you can see as time goes on, after a while, it's not going to be moving to the right, and it's going to start being pulled towards the center again. So that's like it's under the influence of gravitational force there. Everything's being pulled towards that central time axis right there. Okay.
I have a question.
Yes.
How is it that rockets work? So when we shoot it out in space, do they follow a geodesic, or does it just like hit something?
Once it's out in space, well, the thrust is going, that's another force that's a non-gravitational force. So it wouldn't be on a geodesic while it's thrusting, but anything that's just under the influence of gravity. So something falling towards Earth, when a satellite, is starting to fall towards Earth, but it hasn't hit the atmosphere yet, the atmosphere would be another force. Or once you've blasted out of the Earth's gravitational zone, or even if you're still in it, but then you turn off the thrusters and you start, maybe you're partially orbiting, but you're still heading away from Earth, then that would be along a geodesic. So anytime you're just under the influence of gravity, you're going in the most natural way possible. And the fact that you see things that were initially heading apart come back together and maybe collide with each other, when I throw something up from the Earth, it comes back down and hits the Earth. That's a consequence of being in a region where things that look like they're going away from each other can just, following the most natural paths possible, end up back together. And I think Einstein originally had this intuition in that if you jump off something and you're in free fall, all of a sudden it feels like there's no forces acting on you. And he sort of took that literally, the fact that when I jump off a building, hopefully there's something to catch me at the bottom. In some sense, it's like I've been feeling all the forces because I'm being pushed up by the surface of the Earth. But when I'm in free fall, I feel like I'm doing the most natural thing possible. And so that was the natural state that everything was going to be going in the universe along these geodesics in curved spacetime. So just like in elliptic geometry kinds of spaces, objects that are originally sort of moving in the best sense that we can make them go parallel to each other are eventually going to get closer and closer to each other and collide. It's also true that in hyperbolic spaces, if I start two objects here, I'm calling them A and B, and I'm imagining this is my space axis here. They live in a one-dimensional spatial world, and this is the time direction. If I start them going parallel, they're going to get farther and farther apart. In other words, if they stretch a string between themselves, they're going to see the amount of string required is greater and greater as time goes on. So in a hyperbolic geometry, at least in 2 dimensions like this, it would cause objects to apparently accelerate away from each other. Now that doesn't sound like gravity, but we'll see that this happens actually naturally in gravity if we get there today. Okay, so the idea, if we think of lines that are initially parallel, lines that start parallel in a flat space, stay parallel. Lines in an elliptic space that has elliptic geometry get close. If they start parallel, they end up getting closer and closer together as they're continued. In a hyperbolic space, if we start lines, there they are again over here. Those two lines that started parallel to each other, as they're continued, they become non-parallel as time goes on. So just looking at different shapes, of course, the surface of Earth has an elliptic geometry. The surface of an orange has an elliptic geometry. The Pringles potato chip has the classic hyperbolic geometry. Holly leaves have hyperbolic geometry. You can imagine if you tried to draw a circle centered at a point somewhere here and you drew that circumference would be wiggling up and down. So you get too much circumference compared to your radius. That's a sign that you're on a hyperbolic surface. Okay, there's some kind of lettuce that has a very hyperbolic surface. Whenever you draw a lot of a hyperbolic surface, you tend to see all these curves like ruffling over on each other. So that's how you, at least for two-dimensional surfaces, we're talking about 4 dimensions, but we got to use our imagination here. Here someone has crocheted a surface that has hyperbolic geometry. And notice it sort of looks flat at the beginning, but then it starts to get more and more tortuous as you get out from the center. Okay, there's a Mathematica representation of something that's like, oh, just like the Pringles chip does, only one up and down as you go all the way around. This one goes up and down, I guess, 3 times as you go around. The Pringles chip goes up and down twice as you turn around in a circle. Okay, so again, we're not concerned about these nice simple geometries for space-time. We should be thinking about space-time, not just space, but space-time as having a local geometry that can change as time goes on. And I keep checking the time because it seems like I've been talking for longer than usual, but that's just because we haven't stopped to do a worksheet. Okay, so here's a smooth surface that doesn't have a regular or homogeneous shape. And we're only going to be concerned with the surface of this. We're not thinking of it as a solid body, but just a surface. Okay, so it's not a sphere. It's not a Pringles potato chip. It has a kind of geometry that varies as you move around on the surface. And we just want to get kind of used to thinking about whether the geometry at a certain point is elliptic, hyperbolic, or as flat as we can tell with our eyes. You can't really measure flats at one point in between elliptic and hyperbolic, so it's kind of hard to see if something's perfectly flat. What do you think if you get the sense of where this point P is? It's sort of on the surface where this surface is just starting to turn over. So this is called a Klein bottle, and it's a surface where if you follow the surface, you go into this tube, and the tube comes out of the side of the Klein bottle, although you're not supposed to think of it as intersecting, and then you'd be inside the tube there, and you'd end up stuck inside this bulb part in there. In any case, we're just concerned with the curvature of the surface. What do you think for P here? Is that a point that would have elliptic, as best you could judge, hyperbolic, or flat geometry? And remember, what we're thinking of is the key, at least for two-dimensional surfaces, the key thing we're envisioning is that if you're in a region of elliptic geometry, if you head away from a point, at least the way it's embedded in our three-dimensional space, if I head away from a point along a certain line, maybe I go down as I head in this direction. And then as I head in the perpendicular direction, I'm also heading down. That's like the surface of a sphere, whereas that Pringles potato chip, if I go down in one direction, if I go in the perpendicular direction, I go up. So that's what we're looking for here. It may not be perfect, but as I head, I should point with this, as I head in this direction around there versus in that perpendicular direction there, do you think I'm more or less curving in the way of a sphere or in a something hyperbolic? You might think, well, I don't, maybe I put this at sort of a confusing point. What if I move the point up here where I'm pointing right now? What do you think about there? More spherical or more Pringle potato chip? It looks over here clearly spherical. It might be getting a little bit confusing over there, but I was thinking of it as still being an elliptic kind of geometry. Whereas at this point, where we're sort of just on the inside of that edge, we've come around the edge and we're heading into the inside of the bottle. As I move in this direction, maybe in the sense of my slide, I'm going from down to up in the direction of the slide. Whereas as I come around here and go over the edge and down to the bottle, I'm actually going from, around in this direction. I should do it where the camera can see me. So in one sense, I am going around and up like this, whereas if I go, I'm getting confused about how to draw this with my hands by looking backwards. If I go in the other direction, I'm sort of curving downward. That's a little bit hard to view there, but I was trying to show a surface that we're probably not familiar with and just think about the local geometry at each of these points. Here's that donut-shaped torus surface. We're just imagining the surface, and if I imagine, for example, this point out here, this would be a point where we would say there's locally elliptic geometry, because as I go left, right, I curve towards the back of the screen, if you get what I mean by the back. And as I go top to bottom, I'm also curving towards the back of the screen. So I'm curving in the same direction when I go in the two perpendicular directions. Whereas if I look at the inside of the torus, if I go up, down, right, along this, geodesic right there, I'd be curving from the front to the back of the screen there. But if I go around the perpendicular direction there, I would be curving from the front back to the front of the screen. So in one case, it's coming out of the screen, in the other case, it's going back into the screen. That's the hallmark of hyperbolic geometry. And on this yellow line right here, it's right at the boundary between a region of hyperbolic and elliptic geometry. There, it's locally flat, right at that boundary region. So you can kind of imagine, look, the surface of this donut kind of looks like what this surface looks like around that edge where you're going to the inside of the bottle, right? Kind of looks like part of the donut there. And so if you're on the inside of the donut, you're in the hyperbolic region. If you're on the outside, you're in the elliptic region. Right on the edge where it transitions, there's probably a locally flat region. Okay? There's another hyperbolic one up there, right? You're going back to front to back as I go that direction, but if I go in the perpendicular direction, I'm going front, back to front again. Take some practice to think about those. Uh-oh. Hopefully I didn't mess it up. Okay, enough with that. Oh, this one was to point out, I think this is the last one. Over here, what do you think about the geometry? Looks kind of like a cylinder. What do you think the geometry of a cylinder is? Elliptic, hyperbolic? Yeah, Jack is saying flat with his hands. Even though we, in common language, we would say, oh, there's a curved surface. In the sense of intrinsic curvature, we'd say it's perfectly flat there because it's just like a flat piece of paper that's been rolled into a tube, and it kind of looks like a cylinder, at least it's best we can tell at the region that I've labeled there. Okay. Here's a space-time diagram with some world lines shown on it. What do we mean by curved space-time? Well, instead of this diagram lying completely in the plane, it might have some bumps in it, or it might curve into a complete sphere or some other shape, right? So we have to draw now those X and T lines. And again, this is just for a one-dimensional world. We can't visualize a two- or three-dimensional world because we can't show a curved three-dimensional surface, and much less can we draw any four-dimensional surface, because to draw a curved three-dimensional surface, you kind of need 4 dimensions to visualize that, and our brains just don't do that. Okay, so at least for two-dimensional spacetimes, elliptic geometry causes objects to accelerate toward each other. Hyperbolic geometry causes objects to accelerate away from each other when they're initially going in the same direction. And flat geometry, neither. They sort of stay right next to each other, don't increase or decrease. Now, let's just try to figure out what the geometry of space-time looks like near Earth. And again, we can only really envision this if we make our world one-dimensional. So the Earth is, well, the surface is two-dimensional, our world is three-dimensional. I'm going to imagine our whole world is, I've drilled a hole through the Earth, right? And let's imagine there's no atmosphere to slow us down. We've taken all the air away, right? And we're going to drop some objects, and they're only going to move along this line that goes through the very center of the Earth, okay? I'm going to call that the x-axis, so plus x is to the right there. And I'm going to imagine, if you haven't taken any physics before, you might have to hold your breath here a little bit. But this is what the force is on an object. Now, I'm imagining what the force on an object is, the gravitational force, and therefore the acceleration that Newton would attribute to that object. The force, once you get far away from the Earth, way over out far away from the Earth, the force should be small, and therefore the acceleration is small. As you get closer to the Earth, the gravitational force, according to Newton, gets bigger. And then once you start getting inside the Earth, the force gets smaller and smaller and smaller. And of course, if you're just sitting at the center of the Earth, there's no force at all because you're being pulled equally in all directions. And so at the center, there's got to be no net force because the Earth can't pull you in any direction by the symmetry. Same on the other side. Now let's imagine we release two objects very close to each other, but just at slightly different x positions, right? So maybe I'm out here in this region and I say, I'm going to release one from here, and then I'm just going to go a couple of inches above it and release another one over there. What's going to happen to their separations as time goes on? Does it? Why? And Everett's saying they're going to get farther and farther apart. Why is that? Yeah, the one that's closer. So if I drop an object from rest here and just a little bit at a different point in space there, their separation as time goes on is going to get bigger and bigger because the one that's closer to the Earth has a greater acceleration. It's going to start moving away from it faster. The one that was farther is always going to be a little bit behind. So two objects that initially had the same velocity, I put them at rest, get farther away. That sounds like hyperbolic geometry of space-time over here. Similarly, inside the Earth, we can imagine being in here, and I drop two objects that are separated by a small radial difference. What do you think about there? Closer together or farther apart as time goes on? Closer together, because in this case, the one that's farther from the center has the bigger force, and so it's going to be moving, speeding up faster to get closer to the other one. And so that sounds like an elliptic region. Okay, so nearby objects with the same initial velocity get farther apart with time outside the Earth. And then in that region, we've sort of made this artificial one-dimensional world out of the Earth. Nearby objects inside with the same initial velocity get closer together. That sounds like elliptic geometry. Let's try to envision, and I know we're just about out of time here. Let's try to envision a space-time that has hyperbolic geometry at one end. So we're going to imagine an x-axis, and we're going to put a t-axis on it. And I've got to have elliptic geometry in the middle, hyperbolic geometries on the outside, and think about what would happen in that surface. So let's draw what that surface would look like up here. Couldn't find a picture of what, so I had to draw one myself. Here's a curved spacetime. Okay, so it's kind of a strange surface. But notice the local geometry here is elliptic. It looks like a part of a spherical surface, right? And notice over here, although it's curving upwards as I follow this ridge there, it would be curving downwards as I went in the perpendicular direction. So this is a region of hyperbolic geometry when you're on the kind of neck, transition to the neck of the wine bottle, if you think of it that way, right? And I'm going to imagine this space, instead of going around on itself like a sphere, it just keeps continuing. So it's like a rolled up scroll that just gets rolled, continues, and it never comes back on itself ever again. So if you drop two objects, you know, one may be on this side of the interior of the Earth and one on this side of the interior of the Earth, and you watch as time goes on, that's going up in this figure, what's going to happen? Well, it looks like they'll accelerate towards each other, but really they're just following the most natural kinds of paths that they could. They're following a geodesic that kind of looks like a great circle there. If I drop an object, two objects out here in the hyperbolic region, they're actually, you know, sort of gonna, again, they're spiraling around this thing in the direction they're shown there. It's hard to describe this surface, but they're actually gonna get farther and farther apart as they perhaps move in. So I might have given them a little bit of an inclination to go in and they spiral in, but as they spiral in, they would get farther and farther apart. And as we get farther and farther and farther away from Earth, way out there, we're going to asymptotically approach flat geometry, and that's where the Earth's gravitational effect has zero effect anymore. So flat space-time is that Minkowski space-time, which is just like a cylinder. As a cylinder is as good as a flat sheet. And amazingly, we're just about to the end of this kind of presentation. I'll probably pull it all together at the beginning of tomorrow. But my goal here was to just give you a picture that you can bring up in your mind of how Einstein is using a curved spacetime to mimic the effects of gravity, and thereby saying that gravity is not a force like other forces. It's not picky. Everything under the influence of gravity does the same thing, and therefore, instead of thinking of it as a property of the objects and some force between it, we can alternatively think of it as a property of space-time itself, and the objects, doesn't matter what the objects are composed of, are all going to follow the same trajectories. If they followed different trajectories, given the same initial conditions, we wouldn't have been able to do that. So that's kind of a pictorial way of thinking about it. Tomorrow, let me just go to the last thing on the outline here, is to show you a few pictures to touch base with some things that we might be hitting in the philosophy class. The idea of the expanding universe. What does it mean for space to expand? You read about that in Lepoidovin. The Big Bang and the Big Crunch, we also read about that in Lepoidovin. How might these pictures give you some idea of how you could perhaps travel backwards in time? We'll talk about that later, even in the context of special relativity, if you could travel faster than light. And the idea of wormholes, at least the last time we taught the course, some people talked about wormholes in the class, and we want to be able to visualize what that means. So we'll do those tomorrow.